the question of how position, velocity, and acceleration are related is something that often comes up when you are interested in motion. All right, for example, if you were trying to send somebody to the moon, to land on the moon, to build a moon base, to walk on the moon, you would have to know the way that your spacecraft moves through space. All right, so to understand the motion, to be in control of what's going on, you would need to know how the position, velocity, and acceleration are changing, how they're related. Okay, if you were interested in how a population or an economy grows, how a stock price fluctuates, you would be interested in how the price evolves, how the rate of change of the price evolves, and so you could see that there you'd have a similar situation. We wouldn't call it velocity or acceleration, but it'd be the same idea. You'd have rates and the original price variable, okay, and or if it was population, but the point is you've got these variables that are describing how it's changing, okay. So we have a name for this field, this subfield of physics, this question. Equations that relate these variables are called kinematics equations. Now the name is not so important. What's important is I'm going to give you an example of kinematics equations, and we're going to use them a lot. Okay. In this class, we will only study the kinematics equations for a nice simple constant acceleration. Okay, does that mean that, why are we doing that? Does that mean that nothing in the real world has a variable acceleration? Of course that's not what it means. In the real world, you can, when people drive cars, they press the gas pedal, they slam it to the floor, then they ease it back, then they press it a little more, then they brake. All right, so we all know that you can have accelerations that are increasing, decreasing, becomes negative when you decelerate. So there's very complex accelerations in the real world. However, it would take too much mathematics to study those. All right, for the sake of this class, we're only going to study constant accelerations. Now it turns out that there's lots of situations that have a constant acceleration, which we'll soon find out. So this is actually really useful. Okay, so what I'm going to do on the next whiteboard is I'm going to write the kinematic equations for a constant acceleration, and then we will talk around those, talk about that. Okay, so here we go. Kinematics equations for a constant acceleration situation. Okay, so the it'll turn out that the change in x will equal the following, and I'll define all these variables. Change in x is v naught delta t plus 1/2 times the acceleration times delta t squared. The delta x is also equal to, there's going to be 4 of these, okay, and so let me just write them down and then we'll spend some time talking about them. And delta v is a delta t, and delta v squared is 2a delta x. All right, let me now specify the variables in case something was unclear. So v naught, that means the initial velocity. Okay, vf, that means the final velocity. Okay, and I should be clear that x is position. Let me go ahead and write that. X is position, a is acceleration, and v is velocity. Okay, did I get all the variables? I believe so. T is time, right? T is time. Okay, so there you have it. Now, you're going to want to familiarize yourself with these four equations, and you learn to love them and use them a lot because they come up a lot. Okay. Before I use them, let me show you where these came from. All right. So that you see that we didn't just make them up. All right. Now, let me start with the third one. All right. So remember when I told you that I gave you the definition of acceleration. I said acceleration, I'll put this on the left, was delta v over delta t. Now, do a cross multiplication or solve for delta v, whatever you call it. So if you do that, you'll get delta v is a delta t, right? So the third equation is nothing more than rearranging the definition of acceleration. All right, well, that doesn't sound so bad. Okay. Now the second one, it's a little harder to see, but it's a rearranging of this equation. V average is delta x. It's kind of like the definition of velocity. Okay, if I cross multiply with that equation, I will get V average times delta t is equal to delta x. Okay, so that's where the second one comes from. Now, why did I call it V average instead of V? If you use that equation when the velocity is not constant, okay, like in an accelerating situation, delta x over delta t will only equal the average velocity. Okay, now the question is, why is the average velocity equal to what I have in parentheses on the second equation? Why is it equal to v naught plus v final over 2? I'm not going to be able to completely explain that, but let me show you why it makes sense. Okay, so what is the average of, let me talk about an average, because we're talking about average velocity. So let me give you another example of an average. So suppose I wanted you to average the following numbers. Suppose I wanted you to average 0, 1, 2, 3, and 4. Okay, now go ahead and average those with a calculator, whatever you want to do. Can you see that the average is going to be the number in the middle? Can you see that that's equal to the first plus the last divided by 2? Okay, if you have numbers that are equally spaced, the average will be the number in the middle, which is equal to the first and last divided by 2. Okay, this only works, it doesn't work for every set of numbers, it only works if you have numbers that are changing at a constant rate. But isn't that exactly what we have if we have constant acceleration? Doesn't that mean that the velocity is changing at a constant rate? Okay, so if you were to, imagine you were writing down the velocities for a constant acceleration. Well, you start at v naught, and then you have v naught plus something. I don't know, let's call it plus k, and then v naught plus 2k, etc., all the way to v final, right? And then somewhere in the middle of this list, there'll be the average, but the average we know is going to be the first plus the last divided by 2. Okay, so that is, I can't give you the perfect rigorous explanation, but that's gives you an idea why this piece right here is the V average. Okay, so that explains, I've explained the second and third equations. I'll leave the first and fourth as an exercise, but let me just tell you that you can use the second and third to derive the first one by eliminating V final. Okay? And you can derive the last one by eliminating delta t from the third one and the second one. Okay, I'll leave those as an exercise. Now, the derivations of these formulas are not that important, and if you had calculus, they would be a lot easier. Because this is not a calculus class, we don't emphasize the derivation. Okay, but you could go a long way towards seeing where these come from. Okay, so let's do an example of how we'll use these. Okay, so how about this example? A rocket is fired in space, giving an acceleration of let's say 3 meters per second squared for 10 seconds. How far does it go in that time? All right, that's a valid question. Now, if you remember my plots, you would know that the plot of position versus time is going to be a parabola. So you might say, well, that's kind of complicated to figure out the height of the parabola at 10 seconds. Okay, and fortunately, we don't have to rely on parabolas and guesstimating their heights. We have these kinematic equations, which is the algebraic equivalent. Okay, so let's first write down what we know. And let me add one more thing to this. Let's say, so assume initially the rocket was at rest. Okay, so here we go. When they say that, what that means is that the initial velocity was 0. Okay, the acceleration we know is 3 meters per second squared. We know how much time passed within this process, 10 seconds. And what are we looking for? We're looking for delta x, basically, right? All right, so what I would use to solve this one, go back, look at those kinematic equations, and the very first one you'll see is going to be wonderful for this problem. I'll write it out again. Okay, so let's plug in what we know. So 0 times 10 plus 1/2 of 3 times 10 squared gives 150 meters. All right, see how that works? Okay, let me do another example. How about a car, let's see, a car slams on the brakes. A car slams on the brakes and decelerates at 5 meters per second squared for 15 meters. Okay, what is the final velocity if it was initially going at 20 meters per second? All right, so you're slamming on the brakes, and I didn't even give you how long it slammed on the brakes for. All I told you was that it moved 15 meters. Okay, so let's see if we can work this one out. So first, let's summarize what we know. So the initial velocity was 20. The acceleration was -5. The change in disposition was 15 meters. And what are we looking for? We're looking for V final. Okay. So you'll notice that the last kinematic equation will be very helpful for this one. Delta V squared equals 2a delta x. Okay. Delta V squared, if you were wondering what that means is V final squared minus V initial squared. That's what's equal to 2a delta x. Okay, so that means V final squared equals V naught squared if I move it to the other side. Okay, so V final is plus or minus the square root. We don't want to assume it's plus. Now we know just from common sense that if you slam on your brakes, the car is not going to go backwards. So we know it'll be the plus solution, but I just wanted to mention that sometimes it will be the negative answer. Okay, so square root of, and then 20 squared plus 2 times minus 5 times 15. Okay, and let's see, you can work that out and I'll work that out as well. So 20 squared minus okay, so square root of 250 and so that gives about 15.8. It started out at 20 meters per second, and after braking it was going 15.8 meters per second. Alright, isn't that cool? So we can do all kinds of problems now using our kinematic equations. Okay, what about, let's do one more. Well, let's do one that uses all of the kinematic equations, and then I'll show you how you can tell which kinematic equation to use in what situation. All right. So how about this one? In a drag race, after the light turns green, the racers went from a velocity of 0 meters per second to 30 meters per second in 4 seconds. All right. How far did they travel down the track? Okay, we now, if the velocity was constant, it would be velocity times the change in time, right? But here the velocity is far from constant. So how in the world would we solve this one? We know the time. Well, let's summarize what we know. Okay, so we know the initial velocity was 0 meters per second. The final velocity was 30 meters per second. The change in time was 4 seconds, and we're looking for delta x. Okay, for this one I would use this one. Delta x is equal to v naught plus v final over 2 delta t. All right, and so that would give 0 plus 30 divided by 2 times 4, or 15 times 4, or 60 meters. Okay, that's how far they went down the track. All right, pretty cool, huh? And then our last one, to use the last remaining kinematic equation. What is the final velocity if a jet going 100 meters per second undergoes an acceleration of 5 meters per second squared for 3 seconds? All right, so let's summarize what we know. So the initial velocity is 100, the acceleration is 5, the change in time is 3, and we are looking for the final velocity. Okay, so I would use this kinematic equation. Delta V is A delta T. All right, so that means V final minus V initial is equal to A delta T. So V final is V initial plus A delta T, which gives 100 plus 5 times 3, which gives 115 meters per second. Okay, so study those 4 examples and do other examples and familiarize yourself with the kinematic equations. Okay, let me end with this. You may be wondering what kinematic equation to use for specific problems. How did I know which one to use? Okay, for all of the examples, I would suggest writing down the information that you have. Okay, you will often not have, you'll often be missing something, or you won't care about something. Okay, that is how you can tell which kinematic equation will be the most useful. All right, for example, going back to our list, okay, notice that the first one is the very first kinematic equation. Notice that this one is missing. It's missing. Have you noticed there's no v final in the first one? Okay. Now, isn't it possible that you might do a problem where the problem doesn't tell you what the final velocity is? Of course. All right. If a problem didn't tell you what the final velocity is, wouldn't you want to choose a formula that didn't expect you to know it? Okay, so now you know when to choose the first one. Okay, look at the second one. Notice that the second kinematic equation is missing the acceleration. Okay, again, it's obviously possible that a question might not reveal to you what the acceleration is. In that case, the second one would be a good one to choose, okay, because it's not expecting you to know it. All right. The third one is missing delta x. Okay. If you don't know how much the positions changed, use the third one. And then the last one is missing delta t. If you don't know how much time elapsed, use the fourth one. Right? By the way, there's a certain class of problems that will have the acceleration implied even though it appears like they didn't tell you what it is. Okay, and that is the example of free fall. In free fall, it turns out that the acceleration for free fall is always approximately 9.8 meters per second squared. You can take that to the bank. Okay, if they talk about a skydiver, a penny falling off or thrown off a bridge, something like that, you can assume the acceleration is 9.8 meters per second squared. Okay, now if you define the y-axis to be up and the downward direction to be negative, of course you'll have to use minus 9.8 meters per second squared in your calculations. All right, this often goes by the name of G for gravity. Okay, so you'll see people use, such as myself, use G in the kinematic equations where you have A. Okay, sometimes people are skeptical that the acceleration is always the same number. Okay, this means that if I take a grand piano and I take a paper clip and I drop them both from the same height, they're going to accelerate the same amount and hit the ground at the same time. If you have a hard time believing that, I encourage you to get something heavy like an old textbook and something light like a paper clip and hold them each in each hand and then drop them both from the same height and convince yourself that indeed the heavy and light objects hit the ground at the same time.